Happy Monday afternoon. Two announcements. First, hoping to start your exams tomorrow. So I'm hoping to have them done by the end of the week. So just keep an eye up on Canvas. Second, October 31st is a Thursday. I will not be here. I will probably just post a video of the problems or something. I haven't actually looked at the schedule. Actually, have it. I'll be sure. See what we're doing. Yeah, so I will probably just post a video for you to watch. Either that, or what I'll do is kind of come in the next day, see how far I get, and then just do a video of the problems that remain. Something along those lines. So we won't lose any time. We're finishing up with the exponential and logarithmic derivatives, right? So as a reminder, what would that derivative be? What's the derivative of b to the u? What is it? You're missing one thing. You're missing one thing. You forgot chain rule. So again, just the general exponential. So look at this function. What are we going to have to do? What's the first rule we have to use? Quotient rule. Now I have to take the derivative of the numerator, which is what? So what rule would we be using overall to find the derivative of the numerator? All right, each term individually, so take the derivative of the first term. What is it? So ask yourself always, what type of function is it? That's an exponential. Power is x to a power.
Okay.
All right, let me rephrase that. Power is x to a number. Exponential is a number to a function. So we use the exponential rule, which is up there. So what is this derivative? What's the rest of the derivative?
Plus 1.
Minus. Now derivative of the denominator, how are you going to do it?
Times 2 2x to 2 times ln.
And then over denominator squared. Now it's just a matter of simplifying this. Let's see. There is a 2 to the x squared common. Oops. 2x log 2. Lower 2 to the x squared. And let's do this. X squared log 4. That'd be better. There is another simplification that could be made. Common, x to the 3x squared. Could factor out, leave with log of 9 minus log of 4, which would be log of 9/4. But then that looks like a compound fraction. So is that a simplification I really want to make? Personally, no, I don't. So at this point, I'm just going to rewrite the terms. And call it a day. kind of function are we dealing with? So glad you said that. Because that is a very common mistake. That's not a product.
Is that ln of code?
Remember, ln by itself is nonsense. It makes no sense whatsoever. Just like cos by itself would make no sense.
Oh, you see code like that. Okay, never mind.
It has to be of something. So you can kind of think of ln as an operator. Because it's operating on something. So having it by itself doesn't make sense. So it'd be what kind of function?
Logarithm.
What's the derivative of log function? So do the general derivative. What was that?
1 over u.
You forgot chain rule.
I thought general didn't include chain rule.
No, general does include chain rule.
Okay, then 1 over u and then times u.
Times u.
The derivative.
U prime over u. Yeah, general rule involves the chain rule. The specific rule wouldn't. So we know that that's going to be the derivative form. So what kind of function is u?
Cos.
What's the derivative of cos?
Negative sign. Oh, wait. Is that negative 10?
Are you asking me?
It's negative 10.
Negative tangent of x. I'd be very sad if you left it with negative sign over cosine. Kind of function.
Exponential.
What is the exponent? What kind of function?
Trigonometry.
Which one? Trigonometric. Which one? So what is its derivative? And now what is the derivative of 5 to the u? No simplification. Well, I mean, I suppose you could. Suppose you could write it that way. I don't know what purpose that would serve, other than it looks nicer. It's subjective.
So I'm saying it.
I'm staying with the first one.
Kind of function.
Product.
Yep. And we have to use product rule. Right. Unlike when we were dealing with polynomials, you could expand it out and avoid product rule. Now here we don't have a choice. Second times derivative of the first function. What kind of function is it? Bless you. Exponential, specifically the natural exponential. Remember, derivative of e to the u would be u prime e to the u. What kind of function is the power? Or the exponent? Scalar multiple of a power. What is its derivative then? Plus second times derivative of the first. Kind of function are we dealing with? The cosine. What kind of function are we taking the cosine of? Power would be better. You're not wrong with quotients. Just to wind up with one of your terms being 0 anyway, because the derivative of 1 is 0. What is the derivative then of 1 over t?
Negative t to the negative second power.
So negative 1 over t squared. And derivative of cosine is negative sine. Negative times negative. Now we just rewrite it. The question is, do I want to put that all over the same denominator? I think I do. That's not t cubed. dt squared in the denominator. We would have an e to the 5t squared common as well. But for now, let me just write it this way. Second term has 1 over t squared. First term doesn't. So the common denominator is t squared. So you could write it that way, by factoring out that e to the 5t squared. A more common way you'd see this written, however, would be this. That is definitely the more common way of seeing it. So I'll just keep it like that. We good? No questions? Exponential derivatives are probably the easiest derivatives that you're able to do. Well, that just leaves one type of function left. That's the inverse trig. But we need a few tools before we can even tackle that. Specifically, circle. Is a circle a function? It has a relation, but it's not a function. Right? The relation would be x squared. If we're setting it at the origin, x squared plus y squared equals r squared. But if you pick any point on the circle, doesn't it have a slope? At that point, you can draw a tangent line and find the slope. Well, how would you find what that slope is? You have to find dy dx. So how do we find slope of an implicitly defined function? That is what we have to look at next. It's implicit differentiation.
How different is this from normal differentiation?
Not very different at all.
Okay, so
Just more algebra. And I use implicit differentiation to derive the inverse trig derivatives. And then after that would be, with that we also do logarithmic differentiation, so that is all part of that. And then we also do related rates next week, I believe. Next academic week, so starting tomorrow. And that should be it then with derivatives. Related rates is our first application. So we're almost done with derivatives. Then we look at how to apply them. In the meantime, however, you have a project coming up. So the rest of today's class is for you to work on it.